is an update to the previous video I posted, and this is the QR code maze bot driving its way through a maze. If you look at my previous video, I'll put the link in the description. You'll see that I'd created a driver for this robot, and despite the fact the robot could drive its way around the maze, what it was doing was sort of snaking its way down the maze because it was sort of overcorrecting each time. So it would sort of pick up a wall on the left, see it was too close, start to turn, and because the robot was then no longer angled parallel to the walls, the LiDAR readings were not making sense. So what it was basically doing was overcorrecting, and you got this sort of snaking behavior. The other issues with the previous code that I wrote was the corners were quite, the code involved in getting it to turn corners was quite sort of bulky and not perfect. And basically the issue with the previous code boiled down to one thing, and that was the fact that the previous code, so if you go in the GitHub repository, you'll see that was the driver version 2. What that did not do was it did not give the robot the ability to calculate its angle relative to the walls that it's driving down. And what you can see now, you can see it running here, is it's now doing that very nicely. It's not snaking along, it's driving sort of straight down the middle, and I'll show you an example in a moment where I start the robot halfway through the maze, and I deliberately start it off to the left hand side, and what you'll see is it's very good now at centralizing itself. So I'll just stop this quickly so we can have a bit of a look. The GitHub repository, so if you go on github.com/benmay100, go to my repositories, and it's QR code mazebot. There's a bit of a description here telling you of, because I wanted the development journey to be in this this package here. So I've left the version 1 and version 2 of the drivers in the repository, so you can kind of see how I got to version 3. But if you're going to do any testing yourself, I'd recommend version 3. That's got all of the proper wall following intelligence built in, and I'll kind of explain how that works in a moment. So if we go over to the actual code base itself, so I've explained this in detail on the previous video, but in short, basically we've got a package that's got the QR code mazebot, that's got the logic that does the autonomous driving. We've got the QR code mazebot bring up, that just handles the launch of the simulation and all the various nodes. And then we've got the QR code mazebot description, which has obviously got the robot itself, the assets, some launch files, the worlds, etc., etc. So feel free to sort of go in and have a look at those. But what's important and where the changes have occurred is with regard to these drivers. So if I pick up driver 3, which is the one that you've just seen running, first thing you'll notice is what I've done this time is I've separated the robot control logic away from the driver, just to try and keep things abstracted and a little bit easier to manage. So the maze driver now basically has the following functions in it. It's got the callback for the LiDAR subscriber, the callback for the camera subscriber, and then it's got the CMD-vel publisher, and then it's just got this log positions function. That's just something that logs to the terminal some important positions, and I've just got that on a timer just to log those every half a second. You can obviously remove those if you don't want them. The LiDAR subscriber, what that does is picks up a load of important segments of the LiDAR rays, which are used for various different things. And then what it's doing is calling two very important functions. One is the calculate the angular error, and this is the really key change. And the other is to calculate the lateral error. Now on the angular error, I'll come to this in more detail in a moment. This is where we're now using, basically we're taking the LiDAR readings for the right wall, we're taking the LiDAR readings for the left wall. We are then plotting those as Cartesian coordinates. We're then using NumPy to plot a line of best fit. And using that, we can work out the slope of those lines and basically whether the robot is parallel to the walls or not. So it's quite clever how that works. In terms of calculating the lateral error, so basically how close is the robot to the left wall versus the right wall, It's a little bit simpler, but that has also been made a little bit more clever because we now know that the angular error for the robot, if the robot is, say it was too close to the left wall and it starts turning right to make its way back to the middle, the robot's now able to calculate that the robot is skewed off to the right, so the left and right data readings won't truly reflect where its position is. So it uses some trigonometry to basically keep that left and right wall distance position accurate, even when the robot is not, temporarily not parallel to the walls. The callback camera subscriber is the same as it was. That's just using a bit of OpenCV to read the QR codes. And then the command velocity publisher is a little bit different. It's using a switch now. I won't go through all of this because it'll take us a while. But what you will notice if you compared this to version 2 of the driver, all of the self-correcting moves that I had to build before are basically gone, because this robot is so accurate now at going through the corridors, it just doesn't need to do much, if any, self-correcting. So if we make our way just quickly over to the robot control logic, again, I'm not going to go through this in loads of detail. I encourage you to go into the GitHub repository and have a look for yourself, but this is where the magic happens, really, is the calculate the angular error. And as I've explained, what it's basically doing is converting left and right wall LiDAR readings onto a Cartesian plane, applying a line of best fit with some linear regression, and then from that it's working out the slope of the line and therefore the robot's angle relative to the walls. What you'll see, it also does, the robot is trying to estimate at all times its position, and what I mean by that is whether it's in a corner, and whether that's a left or right corner, whether it's just going down a corridor, whether it's coming to the end of the maze, or if it's going down a corridor that it can see opening up to the left. So in other words, if it's coming down a corridor that has a left turn at the end, or vice versa, a right turn. These are really important for it to understand these, because in order for the robot to maintain a correct angular error, there are certain times where it needs to not look at both walls, but just look at one wall. So for example, if it's coming down a corridor that's opening up to the right, that's going to start throwing things off. So what it needs to do is recognize that's happening and just use the left wall slope for its angular error during that period of time. And that's what all of this is doing. If you have got any sort of questions about this, just leave a comment, and more than happy to answer them in more detail. And then, as mentioned, the calculate lateral error is similar to what it was before, but what it's doing here is, as I say, if the robot is not parallel to the walls because it's performing a turn maneuver to get itself central, it's using a bit of trigonometry to make sure its left and right distances are still accurate. And then we've also got this function, which is the establish position function, and this is again looking at various segments of the LiDAR readings to try and establish whereabouts in the maze it is, and it works pretty well. You can tweak and tune the values. Lastly, in the logic, we've got the perform turn function, which is now really simple and short. This was a bit of a monster of a function in the version 2 of this driver. Then here, these functions, I won't go into them, but these are the functions that the calculate angle function uses to do the Cartesian conversions and calculating the line of best fit and getting the slope of the lines, etc, etc. So yeah, lots to look at there. But what I'll do now is let's run the program. And what you'll see is it's going to launch about halfway through the maze, and the reason for that is otherwise it just takes ages to go all the way through the maze. But I'll point out some stuff as we're going through. So let's bring Gazebo over so you can see the robot doing a corrective maneuver there, and getting itself nice and central into the maze. And you'll notice as well, compared to the previous, if you've watched my previous video, how it's really not snaking around. Just down here is RViz, where you can see the camera feed for where it's picking up the QR code. So the robot's picked up the QR code, performing a turn, and what it does this time is once it's performed a turn, it does a little bit of fine tuning using the left wall just to make sure that it's angled correctly. And again, you can see it's coming down the maze really nice and straight now, not overcorrecting, and that's because it's constantly checking its angle relative to the walls. So again, reading that QR code, making its way around. In terms of the turning, I've been able to make that quite a lot faster as well, because the turn function is so much more robust now in this program. In version 2 of the driver, you'll see it has to turn really slowly, because otherwise it misses readings and makes mistakes, but it's now far quicker at turning. It's reading the QR codes more reliably, and as you can see, so far it hasn't had to perform any corrective maneuvers at all. So this one sometimes gives it a bit of a problem, but it looks like it's going to line up quite nicely. Yep, so it's picked that up. And what I tried to do with this maze whilst it's driving down is, you'll see, there's some really long corridor lengths and some shorter ones, and that's to really try and test the program for how robust it is. Another challenge would be a maze with different width corridors. This would be an entirely different challenge, or corridors that aren't parallel, which might be a bit more realistic. So that's probably on the to-do list for the next thing to build. But yeah, as you can see, if you've watched the previous video, if you see the way this robot drives down the maze compared to the previous video, it really is chalk and cheese. So it's coming up to its last bit now, and you see it hasn't had to perform a single corrective move here at all, and that's because fundamentally, when it's driving down the maze, it's staying very central, and it's staying almost perfectly parallel. You can see the readouts here on the terminal here, which give you various information, which is quite useful if you're wanting to play around with the program or make some edits. It should read this now, and then here we go, maze complete. So yeah, a lot learned in this process, and shows how, with a bit of mathematics and some proper wall following functions, how much this can be improved. Please feel free, download the repository onto your own machine. The code is yours to use, and hopefully it's helpful for if you're doing a similar project.